So for the first problem, let us consider these vectors u, v, and w. Okay, so let u be the vector -2, 3, 5, 1, v be the vector 3, 0, -2, 2, and w be the vector 1, 1, -3, -2. So we want to find the distance between u and v minus 3w. And then for the second one, we want to find the projection of w onto v. So for the first one, let's calculate first v minus 3w. So we have here v minus 3w. This is equal to, so let's rewrite all the given information here. You have 3, 0, -2, +2, minus 3 times the vector 1, 1, -3, -2. So this is equal to, let's multiply this -3 to this vector and then let's combine them into a single vector. So that we will have 3 minus 3, comma, so that's 3 minus 3 times 1, and then here 0, minus 3 times 1, so 0 minus 3. And then we have -2 minus 3 times -3, so this becomes -2 plus 9. And then lastly, you have 2 minus 3 times -2, so this becomes 2 plus 6. Okay? And then we just simplify. We will get 0, -3, 7, and then 8. So this is v minus 3w. And therefore, if we want to find the distance between u and v minus 3w, so this will just be equal to the square root of the following. So you have -2 minus 0, okay? So -2 minus 0, quantity squared, plus 3 minus -3. So 3 minus -3 here, quantity squared, plus, and then you have 5 minus 7, quantity squared, plus the last entries, you have 1 minus 8. 1 minus 8 quantity squared. So if you simplify, we have -2 squared, that's 4, plus 3 minus -3, this becomes 3 plus 3, so that's 6 squared, that's 36. Here you have 5 minus 7, that's -2 squared, so that's plus 4. And finally, here you have 1 minus 8, that's -7. If you square it, that becomes 49. So further simplification, you have here 4 plus 36, that's 40. And then you have 40 plus 49, that's 89 plus 4, that's 93. So this guy here, it's square root of 93. Okay? So this is the distance between those two vectors, u and v minus 3w. And then for the second problem in this set, we want to find the projection of w onto u. So in here, you want to find the projection of W onto U. So formula, you have W dot U divided by norm of U squared times the vector U. So take note that this guy here, this is just a scalar. Okay? So let's calculate this scalar here. So W dot U, let me write that. W is again 1, 1, negative 3, negative 2. And then you dot this with U. You have negative 2, 3, 5, 1, 3, 5, 1. And then for the denominator, we just get norm of U squared. So basically, you just square each term and then you add. Sorry, you just square each component and then you add. So you will have here negative 2 squared plus 3 squared plus 5 squared plus 1 squared. And then vector u, it's just negative again. Negative 2, 3, 5, 1. So in the numerator, for the dot product, it's just component-wise multiplication and then you add all those products. So in here, for the numerator, you have 1 times negative 2, that's negative 2, plus 1 times 3, so that's just 3, plus negative 3 times 5, that's negative 15, plus negative 2 times 1, that's negative 2. For the denominator, let's get the squares. So you have 4 plus 9 plus 25 plus 1. And then we copy the vector negative 2, 3, 5, 1. And then you add. So you perform the addition in this fraction and then you multiply it to each of the entries in here. So we have, so negative 2 plus 3, that's positive 1, minus 15, that's minus 14, minus 2, that's minus 16 in the numerator. On the denominator, we have 4 plus 9 plus 25 plus 1. So 9 plus 1, that's 10, plus 25, that's 35, plus 4, that's 39. And we have the vector negative 2, 3, 5, 1. So finally, the final answer will be just the multiplication. So in here, you have 32 over 39, comma, 3 times negative 16, that's negative 48 over 39. Negative 16 times 5, that's negative 80 over 39. And then negative 16 over 39. So this is the projection of W onto U. Okay? Questions? Next problem. So in here, we want to find the area of the parallelogram whose sides are determined by the position vectors 1, 2, -1, and -2, 3, 0. So position vectors, it means that the initial position is the origin. Okay? So, how do we find the area of the parallelogram in tree space if we are given three vectors? So we just get the cross product, okay? We get the cross product and then we get the norm of that cross product, okay? So let's get the cross product first. 1, 2, -1, cross with -2, 3, 0. So you can do the determinant of the 3 by 3 matrix whose first row is ijk, second row is the first factor in here, 1, 2, -1, and the third row is the second factor in here. So -2, 3, 0. So if you do this, we'll get, so for the I here, and then you have minus quantity, and then J, and then plus quantity, and then the K. So for the I, we have this submatrix here. The determinant will be 2 times 0 minus 3 times -1. So 0 minus 3 times -1, that's minus 3. For the J part, we have the submatrix 1, -1, -2, 0. So you will have 1 times 0 minus -2 times -1. That's positive 2. And then for the K part, we have the submatrix 1, 2, -2, 3. So this will be 1 times 3. That's 3 minus -2 times 2. That's -4. Okay? So this will be 3i plus 2j plus, because you have here minus and minus, and then plus 7k. Okay? Or if you want to write this in vector form using the angle brackets, this is just 3, 2, 7. So therefore, the area will be equal to the norm of the vector. Norm of the vector 3 to 7. So this is equal to the square root of 3 squared plus 2 squared plus 7 squared. Or this is equal to the square root of 9 plus 4 plus 49. So if you add them, 9 plus 49, that's 58 plus 4, that's 62. So this is equal to square root of 62. Okay? Next problem. So let L1 be the line parallel to 162 and contains the point 110, and let L2 be the line containing the points -1, 5, 2, and 1, -1, -6. First, we want to write the vector equations for L1 and for L2. Second, we want to give the standard or general equation, so not the vector form, okay, of the plane parallel to both L1 and L2 and contains L2 but not L1. Then for the third one, we want to determine the distance between L1 and L2. So by the way, these two lines, L1 and L2, they are skew lines. Okay, so remember the definition of skew lines. Okay, they are not parallel nor intersecting. Okay, so for the first one, that's the easiest. We know V, or we know L1, so we're looking at L1. L1 is parallel to the vector V1. And vector V1, this is 1, 6, 2. 1, 6, 2. And then it contains the point 1, 1, 0. 1, 1, 0. So L1 has equation. So you have the vector x, y, z. This will be equal to, you have the point 1, 1, 0, put it in vector form, 1, 1, 0, plus t times the vector v1. Okay? So times 1, 6, 2. So this is true, or this one is for any t in R. For L2, contains the points -1, 5, 6, and 1, 5, 2, and you have the other point 1, -1, -6. So this means that L2 is parallel to the vector V2, okay? And this vector V2 is just the this vector V2 is the vector whose components are the difference between the coordinates. Okay? So in here, let's say we have -1, -1 in here, -1, -1, comma. Then 5 minus -1. Okay? 5 minus -1. And then 2 minus -6. 2 minus -6. So if we perform the operations, we'll just have -1, -1, that's -2. Here you have 5 minus -1, that's 6. And then 2 minus -6, that's 8. So we have this vector 2. Okay? We now have a parallel vector. We'll just use any of these 2 points, either this guy or this guy, to write the vector equation for L2. So maybe let's use -1, 5, 2. So your L2 has vector equation given by this. So x, y, z, this is equal to the vector -1, 5, 2 plus, say, let's use the parameter s. S times negative 2, 6, 8. So S here runs, or S here is any real number. Okay? Okay? Next. So in here, we want to find, for the second one, we want to find the standard or general equation of the plane parallel to both L1 and L2 and contains L2 but not L1. Okay? So, to do this, we know that L1 is parallel to V1 and your V1 is given here as 162. We know that L2, or we've calculated that L2 is parallel to V2, and your V2, when we calculated it, it was negative 268. Okay? So here's what we're gonna do. In order to obtain the plane parallel to both L1 and L2, we need a vector, okay? We need a vector that is perpendicular to both L1 and L2, okay? Take note, to give the standard or general equation for the plane, we need a perpendicular vector, okay? So if we want the plane to be parallel to both L1 and L2, then the vector we need to get this plane should be perpendicular to both L1 and L2. Now, we are given these two parallel vectors. Well, one vector parallel to L1 and another vector parallel to L2. I think my first statement there is a bit confusing. So we are given these two vectors here. One vector is parallel to L1, another vector is parallel to L2. And if we want to have a vector that is perpendicular to both V1 and V2, what we can do is to get the cross product of V1 and V2. Remember, the cross product of two vectors will always be perpendicular to both. So that's what we will get. So let say V be the cross product of V1 and V2. So in here, similar to the previous one, we get the determinant of the matrix with first row ijk, second row contains the components of your V1, that's 162, and third row contains the components of V2, which is negative 268. So if we do this, we will have 6 times 8, that's 48, minus 6 times 2, which is 12. This is your I, minus for J, 1 times 8, that's 8, minus negative 2 times 2, that's negative 4. This is J, plus K, plus the one with K, we have 1 times 6, that's 6, minus negative 2 times 6, that's negative 12. So this is our K. If we simplify this and write this in vector form, using the angle brackets. So we have 48 minus 12, that's 36, comma. 8 minus negative 4, that's 12. And we have a negative here, so we have minus 12, comma. 6 minus negative 12, that's 18. So we have 18 here. So this vector V is perpendicular to both L1 and L2. Okay? So V is perpendicular to both L1 and L2. Okay? So taking this as the normal plane, taking this vector as the normal plane or normal vector to the plane, normal vector to the desired plane, desired plane, let's name the plane pi, okay? Then pi pi would be parallel to both L1 and L2. Okay? Next, your pi must contain L2 but not L1. So we will get a point from L2, okay, which is not on L1. And I remarked earlier that L2 and L1 are skew lines, which means they do not intersect. And therefore, we can just get any point from L2. And we are given 2 points here, so we can use it. Okay? Let's use again, let us use the other point this time. 1, negative 1, negative 6. So using the point 1, negative 1, negative 6, the plane would be given, okay, or would have equation so pi. So how do we write this? We have 36 times x minus 1. Then you have the minus 12 here. So minus 12 times y minus negative 1. Then plus you have 18 here times z minus negative 6. Minus negative 6. And this is equal to 0. So this is the standard equation. Okay? This is the standard equation for the plane. Actually, this one is the point normal, not really the standard. This is the point normal equation because you have the normal in here and you have the point. The standard or general equation, we must simplify this. Okay? So we have to distribute this 36, this minus 12, and this 18 to this equation. Okay? So if we do this, let's see. You will now get, we got 36x. So 36 times x, 36 times -1. So you have 36x minus 36. And then for this, you have minus 12y. And then here you have minus minus. So this is plus 1. So minus 12y minus 12. So minus 12y minus 12. And then in here you have z minus -6. So this becomes z plus 6. So you will get 18z. So plus 18z plus 18 times 6. Okay? And that's 108 equals 0. And then we just add these constants here. You have minus 36 minus 12 plus 108. We'll get 60. So we will have 36x minus 12y plus 18z plus 60. This is equal to 0. Okay? And now, this is acceptable. Okay? But let us just reduce this. Look at this. You have 36 minus 12, 18, and 60. They are all divisible by 6. So if we divide everything by 6, okay? If you divide this equation by 6, you will just have 6x minus 2y plus 3z plus 10. This is equal to 0. So this is the reduced form. Okay? This is the reduced form of the equation for the pi. Okay? Questions? For the third problem here, we want to determine the distance between L1 and L2. Okay? So this plane here contains L2. So if we want to get the distance of this L2 from L1, all we need to do is to find the distance between this plane and this line. Or simply, we just need to find the distance between this plane and a point on L1. Okay? So distance between the plane or between L1 and L2. This is just the distance between L1 and the plane pi. But this is just the distance between the point in L1 and pi. So here, P1 will be the given point from L1. Okay? So where P1 is that point 1, 1, 0. Okay? So therefore, the distance is simply, we have the distance formula of pi going to the plane. So in the numerator, you just copy this, replacing the x, y, z with the coordinates 1, 1, 0. Take note that you can use this formula when you have written the equation in its general form. So everything on the left-hand side, on the right-hand side must be equal to 0. So the constant part, if it is not 0, it must be with the variables. Hence, we have here 6 times 1 minus 2 times 1 plus 3 times 0 plus 10. And you have to get the absolute value of that. And for the denominator, you get the norm of the normal vector. So it's the square root of 6 squared plus negative 2 squared plus 3 squared. Okay? So we simplify the numerator. You have 6 minus 2. That's 4. And then here plus 10. That's 14 in the numerator. It's positive, so we can remove the absolute value. For the denominator, you have 6 squared, that's 36, plus 2 squared, that's 36 plus 4, that's 40, plus 3 squared, that's 9. So square root of 49. But square root of 49, that's 7. So 14 over 7, and this is equal to 2. So the distance between L1 and L2, it's just equal to 2. Okay? Questions? Okay? Next. Show that in 3 space, the distance d from a point P to the line L containing the points A and B can be expressed as follows. Okay? So, for example, you have the 2 points. Okay? You have the 2 points A, B. Okay? And that generates line L. So, say this is your point A. This is your point B. Okay? Then you have the line. And then you want some other point here. Okay? This is your point P. And you want to find the distance. So the distance means it's the shortest distance here. So from this point up to this is your distance D. Okay? Of course, this red here, it's your line L. Okay? So how do we find the distance? So what we're going to do, we get the vector from A to B. Okay? Let's use black here. We want to get the vector from A to B. And then we get the vector from A to P. Okay? And then we want to get this vector here. Okay? And find the distance of that vector. Okay? Or we can look at this vector or these 3 points. The point here, not really the point B. Okay? And then we look at the triangle, the right triangle to be more precise. Okay? So we can look at, so you have this point, the point nearest to point P. You look at this triangle here, okay? And you have a right angle here, so you have a right triangle. And then you get the distance of this. But from right triangle, you can have this as your angle, okay? You can have this as your angle. And you can use your SOHCAHTOA if you remember SOHCAHTOA. SOHCAHTOA. So you use the most helpful part, the so, the ka, or the toa. So let us see how we're going to do this. So we let the vector u to be the vector AB. So remember this black part here, okay, from A to B, okay? And then we let V be the vector AP. So from this point up to that point, okay? And we let theta be the angle, the angle between U and V. Okay? Then we know this is our V. Okay? This is our V here. This guy here as a triangle is the hypotenuse of the right triangle. This side here, it's the hypotenuse. And we want to find the length of this leg. This leg here is opposite of the angle theta here. So according to SOHCAHTOA, particularly this part here, so, okay, then sine of theta, that's equal to the opposite over the norm of V. Correct? So the opposite side, it's D, and the hypotenuse, it's the norm of the vector V. Or, we write this now as the distance D. This is equal to the norm of V times sine theta. Okay? But this guy here, let us rewrite this. Okay? Now, the distance D, which was norm of V sine theta, we rewrite this as norm of U times norm of V sine theta divided by norm of U. Okay? So we just multiply and divide by norm of U. And I think we've shown that this guy here, norm of U times norm of V sine theta, okay, this is precisely the cross product of U cross V, and you get the norm. So this guy here is just U cross V, and then you take the norm of that. And of course, the denominator, it's still a norm of u. So this guy here from a result, we proved, okay, in a lecture. In a lecture. Okay. And then you just bring back those guys here. Now, this guy here, we are talking about norms. So we can interchange the two factors here. Okay. But anyway, we'll just have the norm of AB cross AP divided by the norm of AB. Or this guy, as I have said, you can interchange the two factors because you are taking the norm anyway. So AP cross AB, you get the norm of that. It's still the same as the previous line here, over the norm of A. And that's what we have in here. So that's it. We have the formula for the distance. Okay. Questions? Next problem. Now, let v1, v2, and v3 be these vectors here. So we want to show that v1, v2, and v3 form a basis for R3. And then, find the coordinates of 5 to 6 relative to the basis v1, v2, and v3. So first, we know that the dimension of R3, this is equal to 3. Okay? And the S equals the set containing V1, V2, and V3. Okay? Has 3 elements. Okay? So it's enough to show whether these 3 vectors are linearly independent. So we can just show that to show that S is a basis. Or we can just show that these elements V1, V2, V3 span the set R3. We can just show that. So remember the theorem that was discussed earlier. So maybe let's just show that these 3 vectors are linearly independent. So it suffices to show that S is linearly independent. So to do this, Suppose we have K1 V1 plus K2 V2 plus K3 V3. This is equal to the 0 vector. Or we have K1 times vector V1, it's negative 2, 0, 1 plus K2. Vector V2, it's 0, negative 1, negative 1 plus K3. Vector V3, it's 1, 1, 1. This is equal to the 0 vector 0, 0, 0. Then, we can rewrite this in matrix equation form. Okay? Then, we have this negative 2, 0, 1, 0, negative 1, negative 1, 1, 1, 1 times the vector K1, K2, K3. This is equal to the vector 0, 0, 0. Let me check if this is what we need. Of course, the first column will always be multiplied to the first entry in here. Okay? And that means K1 is being multiplied to the vector negative 2, 0, 1. So that's why we wrote this vector in column form. The second column will always be multiplied to the second entry here. So that means your K2 is being multiplied to this vector. Similarly for your K3. So this is the conversion of this equation into this matrix equation. Okay? So it's enough to show that this guy here has determinant equal to non-zero. Because if that's the case, it means that this matrix equation has only the trivial solution. Okay? We need to show that the determinant of negative 2, 0, 1, 0, negative 1, 1, 1, negative 1, 1. The determinant of this is not equal to 0. Okay? We need to show that the determinant is not equal to 0 so that the vector k1, k2, k3 okay, this vector here has only the trivial solution. So that the vector k1, k2, k3 has only the trivial solution. Which means this is linearly independent, or the set is linearly independent. Okay? So that means S is linearly independent. So let's show that this determinant here is non-zero. So indeed, the determinant of -2, 0, 1, 0, -1, 1, 1, -1, 1. This is equal to what? -2 times -1 times 1. That's +2. 0 times 1 times 1. So that's +0. 1 times -1 times 0. That's still +0. Minus quantity. So try to work on the determinant here. Okay. I'm just trying to do the method of augmenting the first two columns here. Okay, and then do this going down, going down, going down, minus going up, going up, going up. Okay, but the augmented two columns here, I'm doing it mentally. Okay, but try to work on the determinant. So now I am on the part going up. We'll have 1 times -1 times 1. That's -1 plus. Here you have -1 times 1 times -2. That's +2. So +2. And then here you have 1 times 0 times 0 plus 0. And this is equal to 1. So 2 minus -1, that's 3, minus 2, that's +1. So this is not equal to 0. Okay? So therefore, this guy here has only the trivial solution, and therefore S is linearly independent. So K1 equals K2 equals K3 equals 0. So S is linearly independent. So S is a basis. Okay? Questions? That's just for the part 1. For the part 2, so for the part 2, we need to solve for the values of K. So for the part 2, we need to find K1, K2, K3 such that you have the previous matrix equation here. So we get this guy here. Okay. So we have -2, 0, 1, 0, -1, -1, 1, 1, 1, multiplied to that vector K1, K2, K3. Okay. We want to find K1, K2, and K3 so that when you multiply this, we will have the vector 5, 2, 6. Okay? But this guy here, since the determinant of this is not equal to 0, this will have a unique solution. And the solution K1, K2, and K3 can be obtained by multiplying both sides of the equation by the inverse of this. Okay? That's one way. We need to find the inverse of this. Another way, maybe it's easier if we try to do the inversion. Okay? We try to do the inversion here and try to find our k, our 5 to 6. So we find the RREF, okay, 201. Remember this, 5 and then 0, negative 1, 1, 2, and then 1, negative 1, 1, 6. Augmented matrix, we find the RREF. So we want to get the identity matrix on this part, and whatever result on the right side here, then those are the coefficients, K1, K2, and K3. So we still need all those knowledge that we've learned from chapter 1. So first, let's interchange row 1 and row 3 because this is already a 1 in here. If you divide this by negative 2, we will get a fraction here and a fraction here. And again, that will complicate our computation. So let's just interchange row 1 and row 3. So we have 1, negative 1, 1, and then 6 in here. Row 2, it's still 0, negative 1, 1, 2. For row 3, we now have negative 2, 0, 1, and then 5. And then we'll make this 0. So we can have row 3 plus 2 row 1. So we just copy row 1. That's 1, negative 1, 1. And then 6 in here. We copy row 2. It's still 0, negative 1, 1. And then 2 in here. For row 3, we have negative 2 plus 2 times 1. That's 0. 0 plus 2 times negative 1. That's negative 2. And then here you have 1 plus 2 times negative, 1 plus 2 times 1. That becomes now 3. And then we have here 5 plus 2 times 6. So 5 plus 12. That's 17. Okay? Let's remove the negative in this entry here. So negative R2. Let's copy now. 1, negative 1, 1. 6. Then here this becomes 0, 1, negative 1, negative 2. And here you have 0, negative 2, 3, 17. Then we make this 0. So we will have R3 plus 2R2. So we will have 1, negative 6. Sorry. 1, negative 1, 1. And then you have 6 in here. Here you have 0, 1, negative 1, negative 2. And then we have 0 minus 0, that's still 0. Or 0 plus 0, that's still 0. And then negative 2 plus 2 times 1, that becomes 0. 3 plus 2 times negative 1, so 3 minus 2, that becomes 1. 17 plus 2 times negative 2, so 17 minus 4, that's 13. Okay? Next step, we want to make this 0 and this guy here 0. So row 1 minus row 3 and row 2 plus row 3. So row 1 minus row 3. So 1 minus 0, that's 1. Negative 1 minus 0, that's negative 1. 1 minus 1, that's 0. Then 6 minus 13, that's negative 7. In here, row 2 plus row 3, 1 plus 0 plus 0, that's still 0. 1 plus 0, that's still 1. And then negative 1 plus 1, that's 0. Negative 2 plus 13, that's 11. And then third row, we just copy it, 0, 0, 1, 13. And finally, the last step, we have to make this 0. So we just add 1 and row 1 and row 2. So row 1 plus row 2 will have what? 1 plus 0, that's 1. Negative 1 plus 1, that's 0. 0 plus 0, that's 0. Negative 7 plus 11, that's 4. And then we just copy second row and third row. 0, 1, 0, 11. And then 0, 0, 1, 13. Okay? This means K1, this is equal to 4. K2, this is equal to 11. And K3, this is equal to 13. Okay? So, the coordinates of this 5, 2, 6, okay? So, the coordinates of this vector 5, 2, 6 with respect to the set S, okay, with respect to the basis V1, V2, and V3, this is equal to these values of K, 4, 11, and 13. So that is our final answer. Okay? Questions? Okay. Next problem here. Let A be the point 5, 1, negative 2, B be the point 2, 1, positive 2, and C be the point 9, 1, 1. Okay? Let these 3 points, let these be 3 points in the R space, in the space R3. We want to show that the triangle ABC is a right triangle. We want to specify the point where the right angle is. Okay? So, for example, you have these 3 points here, A, B, C. Okay? A, B, C. You have a triangle. Okay? This doesn't look like a right triangle at all. But you need to show, if these are the 3 points, okay, you need to find where the right angle is. I'm not sure if the right angle is at C or at B or at A. You have to find it. And in order to find that, you consider two vectors, either A to B and A to C, or B to A and B to C, or C to A and C to B. Okay? And then show that the two vectors are perpendicular. You choose the right pairing. For example, let's say our V1, so this is for item number 1. Let's say our V1, it's the vector AB. Then our V2 will be the vector AC. So same initial point, A1, A and A. Okay? So if you chose this pair, you need to show that V1 is perpendicular to V2. And in this pair, your choice may be a failure, in a sense that it is possible that with this pairing, V1 and V2 are not perpendicular. So this is our first trial. Vector AB, so it will be B minus A. We will have 2 minus 5, comma, 1 minus 1, comma, 2 minus negative 2. So if we simplify this, we have 2 minus 5, that's minus 3. 1 minus 1, that's just 0. 2 minus negative 2, that's 4. And then for the AC, we have 9 minus 5. We have 1 minus 1. And then we have 1 minus negative 2. So in here, we have 9 minus 5, that's 4. 1 minus 1, that's still 0. 1 minus negative 2, that's negative 3. So we have these two vectors now, V1 and V2. We want to show that they are perpendicular. To show that they are perpendicular, it's enough to show that their dot product, remember that? Dot product V1, V2. So V1 dot V2, we want to show that this is equal to 0. Remember that definition? Two vectors are, or remember that theorem? Two vectors are perpendicular if their dot product is equal to 0. So Let's check the dot product. So V1, which was 304, dot this with V2, which is 40, negative 3. 4. Sorry, why is this negative 3? This should be positive 3. Yes, you are correct. 1 minus negative 2, that's positive 3. Thank you for that correction. So you will have here 4, 0, positive 3. So if we calculate the dot product, this is just negative 3 times 4 plus 0 plus 4 times 3. And clearly, we see that this is negative 12 plus 12, and this is equal to 0. So indeed, V1 and V2 are perpendicular. Thus, V1 and or V1 is perpendicular to V2. So triangle ABC forms, triangle ABC is a right triangle okay? And the right angle is at point A. That's the initial vector or initial position here, or the initial point for vector 1 and vector 2. Okay? So it's a right triangle with right angle at A. With right angle at point A. Okay? Therefore, if we fix this drawing, okay, it must be something like this. So this is your point A. Maybe this is your, so this is your A. Maybe this is your C, and your B, it's, let's put it somewhere below. I don't know. Maybe point B is here. But the point here is that these two vectors are perpendicular. Okay? So you have the triangle. So this is your point C. You have the triangle, this guy here. Of course, the orientation is not accurate if you don't have the space. But anyway. For the second problem here, we want to find the area of the triangle. So all we need to do is to find the cross product of these two vectors, and then we get the norm. Correct? That's one way. The second way, you know, this is the base, this is the height. So multiply the length of this by the length of this, and then divide it by 2. Correct? So we can do that. So for number 2, area, this is just the norm of vector v1 times the norm of vector v2 divided by 2. So this is your v1 here, this is your v2 here. Base times height divided by 2. That's the area of the triangle. But you see, norm of v1, that's just what? Negative 3 squared. So negative 3 squared here. Plus 4 squared. You take the square root of this. And then for the norm of v2, you have 4 squared plus 3 squared. You take the square root of that, and then you divide this by 2. But in any case, you just have here 9 plus 16. In here, you also have 9 plus 16. So you actually have square root of 25 times square root of 25 over 2. Or simply, this is 25 over 2. So this is just 25 over 2. So that is the area of this triangle, or this triangle here. Questions?